So welcome again. We have done with the signals. Now we will take the second part. We will try to have some introduction about the system, the way we defined it in a general way. Now we'll see the methodology or the formulation. It will stay the same. Means we will be first of all looking at a qualitative definition of a system, like we did in the signal. Then, since we have to analyze a system, we will be needing a what you call a mathematical model, a mathematical definition of a system, which we will be using later to discuss other things like properties of the system and characterizing how we can actually, for a given property, how we can express, how we define a system, express a system in a particular way. As far as the qualitative definition goes about a system, like we define its signal as something that carries message, that carries information. In a similar way, a system is, let me write it down here for you. A system is a process for which cause and effect relations exist. Fine. It's a kind of a general qualitative definition for a system. The keywords here are cause and effect, and it's true for any physical process. You initiate a particular thing, it will respond, and that response will be an output. So, put in the simpler language, we say that the cause is the input, system input to be more specific. You will give some input to your system, it will respond depending upon what is the behavior of the system, and it will always come with the effect, which will be your output. Right? So I can say a system is something that kind of relates my output to the input. Right? It's a kind of a cause and effect relationship. But then again, we can't only use this qualitative definition because we have to analyze systems like we analyzed our signals. So we have to come up with some sort of a mathematical formulation. Right? So mathematically speaking, a system it may be viewed as an interconnection of operations. In this simple case, it may be a single operation, but since we are generalizing, there may be multiple operations within a system. So we'll say that it is an interconnection of operations that transforms an input signal, which is your cause, into an output signal, which is the effect, such that the properties, simply put, with different properties. Right? You have an input signal, say x of t. You use this signal as an input to your system. System will process it depending upon what is the nature of the system. Then it will come up with an output signal which will be different from the input signal. Right? So you may think of a simple amplifier. You feed an input signal, and what you get at the output is another signal, but that has a high amplitude. It is an amplified version of the input signal. So the properties change. Now mathematically, how we formulate this, we have an output signal y of t, we have an input signal x of t, and we use a factor, let's denote that by h, and h basically denotes the action that the system performs. Right? X of t is your input signal. Let me just write it here. It is your input signal. And y of t, it is your output signal. And h, although formally we say it's the action of a system, is a kind of a system property. Right? Similarly, if you have the discrete time case, you can say y of n, it is h, it's not h into, don't consider it that I am multiplying h with x of t, x of n. It is basically some transformation that is being operated on your input. Ab your transformation kya hai, what is the nature of this transformation? It varies from system to system, and you have to define it explicitly when you're considering a particular system. We'll be taking a very small example, usse thoda clear ho jayega, right? Similarly, we sometimes use block diagrams to represent these transformations. So uske hisab se I may have a system like this. It will have a operation or a system property h, then it will have some input x of t, and it will provide you with output y of t. Right? And x of t and y of t, they will have different properties. Same thing with the discrete time case. System having a system property h, you'll give some discrete time input x of n, and it will give you a discrete time output y of n with different properties. Right? So as an example, if I take we had done a basic operation of time shifting. So if I take a shifting system, that is a system which shifts your input signal. So again, it will have this block representation. It will have a system property h, where it is shifting by k unit. So let's say represented by s superscript k. So whenever you feed an input signal x of m, the system property is such that it will give you an output sequence, output signal y of n, which will be a shifted version of your input signal by k units. Right? So you can say this is the graphical representation, and mathematically y of n is equivalent to h, that is this operator will operate on x of n, the input signal, and explicitly this is the operation, that it shifts your input by some amount, say k. Fine. To further elaborate, let's take a practical example. Let's try and discuss what is known as a moving average system. So it is a system which will have input, which will have output, then there is the system property. Now what this system does is it takes the average of the 3 most recent samples of the signal. Right? So if I have, just to formulate it, so I have an input signal x of n. Right? Now moving average system, it takes the average of 3 recent samples. Now x of n is my current sample which exists at this time. तो जो recent samples होंगे, recent signal samples, एक तो ये current वाला है x of n, then इससे पहले एक that is at time n minus 1, then उससे पहले एक that is at time n minus 2. So your moving average system, it takes these 3 values, the current sample value, the previous one and the one previous to that, and then it takes the average. So if I'm trying to express it, so mathematically it will be y of n, some transformation which will represent by x h that will take place on my input signal x of n in general form. And explicitly the transformation is like this: it will average out the three recent samples, x of n minus 1, then x of n minus 2, right? Now if I am to implement this system, एक तो हो गया general description, like this. It has system property h, you feed an input x of n, it will give you y of n, which will be equivalent to 1 upon 3 x of n plus x of n minus 1 plus x of n minus 2. This is a kind of a general thing, but we need to construct a system which will actually perform this kind of a function, right? We need to see what the individual blocks are. So in this case, if you see this, I'm just taking an example so that you're introduced to a system in a better way, in the mathematical as well as in the graphical way. So you can see there are some operations that are being performed by the system. First one is, you have an original sample, you have to get previous sample. So this is basically shifting operation. Like this is shifting x of n by 1 unit towards right. This is shifting x of n by 2 units towards right. Then we have addition operation, two addition operations, and then you have a division operation. Fine. So if I am to implement this in terms of a block diagram, I will require an adder, that is this block. I will require a time shifter, that is this s to the power k, and I will require a gain multiplier. Fine. Something like this with the gain value in between. Right. So what will happen, I have an input, I always start with the input x of n. From this input I need two more values, x of n minus 1 and n minus 2. So I will use a shifter s raised power 1. So this will give me x of n minus 1. Then I will use another shifter s superscript 2, shifting by 2 units. It will give me x n minus 2. And यहाँ से I have the normal x of n. Fine. Then I need to sum them up. So I will use an adder, a summer block. Add this sample, this sample. Then I need a gain multiplier. So I will use this, multiply this sum by 1 by 3. Then I will get an output y of n. Fine. So in this case, my individual samples, they are appearing in parallel. So I can say that this is a kind of a parallel connection. I can have a same functionality but implement it in a slightly different way. Like this. Again, I will start with my original signal x of n. Then I will first use shifter x n minus, so that I can get x of n minus 1. Then on the same I will use another shifter. It will shift this x n minus 1 by 1 unit, so I will get x n minus 2. Then again I will be using a summer block, that's an adder. Input from here, input from here, and input from here. Then again a gain multiplier. 1 upon 3, and I will get my y of n. So this will be what's known as the cascaded connection, yeah, implementation, whatever you want to call it. So why I did a small example, it basically brings forth some observations. First observation is that a system will always have an input, it will always have an output, which will have different properties. So input has one set of properties and output has another set of properties. Second thing, a system is basically performs transformation on this input signal. Transformation may be simple, like we had a simple shifting system, or it may be a series of operations. That's why I defined it as an interconnection of operations rather than a single operation. Like in this case, it was basically interconnection of 3 operations: shifting, addition, then gain, multiplication. Right? Then another important property is that for every system functionality, like this is a detailed functionality of this system, let me should probably write it. First thing, there will be input and output in a system, that is with different properties. Okay. Second thing, system is basically a transformation of input to output. Transformation may be simple or transformation may involve a series of operations. Right? In general, that is. And then finally, you can have multiple realizations, yeah, implementations, whatever you want to call it, for a given functionality. Right? Yeah, for a given set of transformations. Like in this case, I can also have multiple other connections, but I did only 2 just to put forward the point that for a given implementation, for a given functionality, for a given transformation, you can have multiple realizations, you can have multiple implementations. Right? But like I said previously at the start, that this course mainly focuses on the analysis rather than the realization. So we will be mainly interested in what are the transformations that we can do at the system level. Although we did study some basic transformations like shifting, scaling, yeah, folding, they are basically transformations. Now we will define the systems that perform those kind of transformations. More importantly, what we will be discussing and what we will be interested in is what are the different properties of a system, right? Like we did properties of signals, periodicity was one property. Basically, we did classifications of the signals, but those classifications were based on certain properties like nature of independent variable, like the property of symmetry, wherein we defined even and odd. Similarly, property of what you call that conjugate symmetry was there. Yeah, even the third case, periodicity was there. So these are all properties. Based on those properties, we classified our signals. Same thing here. We will discuss some properties of systems like linearity, causality, stability, and many other. Then we will be classifying systems, yeah, characterizing systems on the basis of those properties. That will be in the upcoming videos.